Hello, I'm Sebastian from the Machine Learning and Computer Vision Lab of the University of Augsburg, and I will introduce our pseudo-label noise suppression techniques for semi-supervised semantic segmentation. The task of semi-supervised learning is to train a model using labeled and unlabeled data together. Current semi-supervised learning approaches utilize the prediction of a model as supervision for the training on unlabeled data, usually referred to as pseudo-labels. This figure here illustrates the iterative pseudo-label refinement method. First, we train a model fully supervised on the labeled training dataset. This model is then used to calculate pseudo-labels for unlabeled data. Next, a new model is trained from scratch, now on labeled as well as unlabeled data together. And afterwards, we can update the pseudo-labels with the new trained model. And this process can be repeated several times. Since the prediction and those the pseudo-labels do not come from an error-free neural network, they are naturally full of errors. Wrong pseudo-labels in the training dataset generally have a negative impact on the training process. This is due to that neural networks can overfit to wrong labels owing to their high capacity of totally memorizing training samples. So it is crucial to manage errors in pseudo-labels wisely. In this work, we do this with three mechanisms. First, we utilize image mixing with a co-mask for this. With this augmentation, individual parts of an image are replaced by another image. Such an augmentation can be seen as perturbation and prevents the model from easily memorizing the noisy pseudo-labels. And the figure here illustrates the augmentation and shows a final image used for the training. Second, we analyze the common practice of pseudo-label filtering. The motivation for this comes from the observation that if all wrong pseudo-labels were not used as feedback at training, the subsequent performance increases enormously, which shows that wrong pseudo-labels do indeed lead to a poorer performing model. The critical question is, how can we identify wrong pseudo-labels? The common idea is to remove pseudo-labels with low confidence from the training and assume that a low confidence correlates with wrong pseudo-labels. The confidence is defined by the output probability after the softmax function of the predicted class of the model. A higher confidence is equated with a higher certainty that the pseudo-label is correct. Our third approach is based on the observation that the confidence of correct pseudo-labels grow faster than those of wrong pseudo-labels over the course of model training. And this can be explained by recent studies on the memorization effect of deep neural networks that show that they first memorize training data of clean labels and then those of noisy samples. Motivated by this observation, we propose a weighting scheme with the aim to assign smaller weights to possible wrong pseudo-labels and therefore reduce the contribution of noisy pseudo-labels at training. We calculate the weight of a pseudo-label from the current confidence value of the student model for the given pseudo-label. Compared to the filtering, the proposed weighting scheme does not have the disadvantage that the resulting pseudo-label dataset is smaller than before, since no labels are removed. To analyze the effect of pseudo-label filtering, we studied pseudo-labels with different uncertainty in more detail. Given the complete pseudo-label dataset, we split it into 10 subsets according to the confidence, taking into account different classes. For example, one dataset contains pseudo-labels for each class with a 10% lowest confidence. Then we performed a semi-supervised learning training iteration for each of the 10 pseudo-label datasets. On the right, we can see the quality of the pseudo-label subsets and the resulting performance of the trained neural network when additionally using the subset for training. And as expected, we can observe that the confidence of the model prediction indeed correlates with the correctness of the pseudo-label. Comparing the final performance when incorporating the pseudo-label subset into a semi-supervised learning training, we observe a weaker correlation. Taking, for example, the pseudo-labels with the 10% lowest confidence additionally into the training, the performance decreases to the baseline model. This shows that those pseudo-labels have a harmful influence at the training. However, this effect no longer occurs in samples with a slightly higher confidence, most probably because strong perturbation already suppressed the negative effect of wrong pseudo-labels. Using the worst 10 to 20% of pseudo-labels additional to the training already improves the performance here. And even more interesting, we can observe that the worst 30 to 40% have an almost equal effect in performance boost as the top 10% confidence samples. This is probably because the correct pseudo labels from lower confidence subsets are samples that the model struggles with. In other words, the correct pseudo labels from lower confidence subsets improve the performance more than those from high confidence samples. High confidence samples are probably more similar to examples from the label training dataset, and correct pseudo labels with low confidence have a higher impact on the resulting decision boundary. To investigate the influence of the individual methods, we performed an ablation study on 3 different datasets: Cityscapes, Mapillary, and Pascal. We also specially assume a scenario with only a few labeled samples, as this presents the greatest difficulty and has a very large difference in performance compared to the model that used the full dataset. There's also a higher number of wrong pseudo labels, which makes the filtering more interesting. First, we evaluate the contribution of the image mixing method. We show on the one hand the resulting performance after a single iteration with additional training on unlabeled data with pseudo labels, and on the other side, the performance when we further apply the image mixing method when training on these pseudo labels. It can be seen that the use of image mixing perturbation in addition to pseudo labels leads to a similar performance boost as the use of pseudo labels in general. To verify that the improvement does not come from the data augmentation strategy, we also trained the fully supervised baseline with the image mixing augmentation. Here we can observe a small deterioration in performance, showing that this augmentation strategy only improves the result when applied to images with pseudo labels, not to images where ground truth annotations is available. In our paper, we also compare the usage of co-mask to cut-mix and show that a co-mask is more effective. Based on the findings concerning the pseudo-label filtering, we removed the most uncertain 20% of each class from the pseudo-label dataset. It can be seen that the performance improves only slightly at Cityscapes and Mapillary, while it becomes worse at Pascal. From the experiments, it can be concluded that a confidence-based filtering does not lead to the hoped for significant improvement. From the results, we finally conclude that the removing of incorrect pseudo labels leads to an improvement, but removing correct pseudo labels leads to a deterioration, and that both effects ultimately overlap. Thus, confidence-based filtering is not good enough at detecting wrong pseudo labels because there are too many correct pseudo labels with low confidence. Third, we evaluate the weighting scheme of pseudo labels. Here we can see that the weighting scheme improves the performance on all 3 experimental settings. We further verified whether wrong pseudo labels indeed have a lower weight during training than correct pseudo labels. Here we found that the weights of the correct pseudo labels were on average twice as high as those of wrong pseudo labels. This shows that the influence of wrong pseudo labels during training is reduced, and therefore an improvement in performance occurs. Further applying the symmetric cross entropy instead of the standard cross entropy loss further improves the performance slightly. Here we show a more complete view of the performance on the Cityscapes dataset when assuming different ratios of the complete training dataset to be labeled. We can see that with our semi-supervised learning approach, we can achieve a similar performance when assuming only 25% of the dataset to be labeled compared to the model that used the whole ground truth labels of the whole dataset. Even when assuming only an 8 of the dataset to be labeled, we can almost fill the performance gap with semi-supervised learning. We further show an example prediction of an unseen image of our semi-supervised learning model that has been trained with only 15 labeled images. To verify if our findings are not specific to semantic segmentation, we also apply our method on the human pose estimation task. The experiments were conducted on the LSP dataset, which contains of 2000 images with 14 annotated joints. For our ablations, we use 1600 images as training set and the rest for evaluation. And similar to semantic segmentation, we can observe an improvement when using image mixing as well as our proposed pseudo-label weighting scheme, while pseudo-label filtering shows to be less effective. Since the findings for human pose estimation are similar to those for semantic segmentation, we can assume that they also apply to other domains and tasks. Thank you very much for your attention.